Welcome back to The Explainer. So let's just jump right in. Have you ever stopped to wonder how a single AI model could possibly master looking at a super high-resolution photograph, flipping through a multi-image gallery, and watching a fast-paced video all at the exact same time? Usually AI models are kind of one-trick ponies, right? They do one of those things really well and completely fail at the rest. But today we are unpacking LLaVA-OneVision. It's this fascinating architectural recipe that actually solved this exact puzzle and brought all three visual formats under one roof.
Here's our roadmap for today. We're going to hit the fragmented AI problem, look at the unified token budget, break down the three-stage curriculum, check out some wild emergent skills, and finally wrap up with open alternatives and trade-offs. Let's do it.
Kicking things off with Part 1, the fragmented AI problem. Before LLaVA-OneVision came along, the open-source vision language landscape was, well, honestly, it was kind of a mess. Totally disconnected silos. You had models that were brilliant at reading text in a single image, and then entirely different lineages of models for processing video. And here's why. Single images are greedy for detail. You need high-resolution tokens, roughly 2,880 of them per sample, just to read text or catch fine details accurately. But video plays by completely different rules. It needs to process a ton of frames to understand time and motion, using maybe 196 tokens per frame. You try to mash those two competing needs together in one system, and boom, you literally blow past the AI's processing limits.
So, how did developers deal with this impossible math before? Basically, they just ignored it. The old approach was literally train one scenario, ignore the rest. You had models like Video LLVA or LLaVA Next that just kind of bolted video onto an image model with some extra training stages, or treated multi-image support as a total afterthought. It gave us these Frankenstein, patched-together AIs instead of one truly unified brain.
Which brings us to Section 2, the unified token budget.
This is the magic key that actually solves the puzzle. It's a deceptively simple hard limit that forces the model to be incredibly smart about how it processes visual info. It's called the token budget. Essentially, it's the total number of visual tokens the LLM is allowed to see per sample. Think of it like a fixed wallet of cash. The AI has exactly that much money to spend on a task, no matter what kind of visual data it's looking at, and it absolutely cannot overspend.
And that strict boundary, it is locked in at exactly 3,000 to 4,000 tokens, period. LLaVA-OneVision forces every single scenario to squeeze into this exact same budget, so the LLM never ever sees a massive batch of data that blows out its context window, which keeps the computing requirements highly predictable.
So how exactly does it spend that same budget differently depending on the media? Well, for a single image, the AI buys detail. It spends about 1,820 tokens for high resolution and text reading. For a multi-image task, it spreads the wealth, balancing across 6 moderate resolution images. And for video, it buys frames. 32 frames to be exact, but at a bargain basement cost of just 81 tokens per frame. The geometric processing totally changes behind the scenes, but the core LLM is still consuming that exact same unified budget. It's brilliant.
Now you're probably wondering, how on earth does it make those video frames so cheap to process? The secret sauce is bilinear pooling. The model affords its strict budget by literally shrinking tokens in 2D space. It takes a 24 by 24 grid of visual patches and smoothly blends it down to 12 by 12 or even smaller. So you're massively dropping the token count, but, and this is absolutely crucial, you're preserving spatial locality, meaning the AI still remembers exactly where objects are located on the screen.
Let's move to Section 3, the three-stage curriculum.
Now, having a clever budget is awesome, but it's not enough on its own. To make this unified model actually work, the AI has to go to school following a strictly controlled curriculum. Otherwise, it gets completely lost, which naturally makes you wonder, what if we mess up the order? Like, what if we just throw it into the deep end and train it on the absolute hardest task, video, first?
Well, it's a total disaster. Training video first causes the model to underfit perception and overfit structure. What does that actually mean in plain English? It means the AI might figure out the timeline. This event happened before that event, but it completely loses the ability to see fine visual details. It becomes visually shallow. Without a strong perceptual base, sure, it can track motion, but it isn't going to be able to read a tiny street sign passing by in the background.
So they use a very specific rule of 3 for the curriculum to prevent that. Step 1 is Stage SI, Single Image Training. This builds a rock-solid perceptual base, teaching the AI to see fine details and read high-res text. Step 2 is Stage OV, where it mixes single, multi-image, and video together, teaching the AI how to handle complex compositional logic. And finally, step 3 is task transfer, tweaking the model for whatever specific real-world job it's actually going to do. By moving strictly from deep perception to complex composition, the AI totally avoids catastrophic forgetting.
Moving right along to Section 4, Emergent Cross-Scenario Skills.
Okay, I absolutely love this part. This is where the strict budget and that smart curriculum pay off in ways the researchers literally didn't even plan for. It's like a magic trick. Out of nowhere, LLaVA-OneVision suddenly developed these 3 massive superpowers. Multi-camera reasoning, meaning it can seamlessly weave together separate views from different driving cameras. Set of mark prompting, you slap numbered stickers on an image and it effortlessly tracks and relates them. And incredibly, it became an iPhone screenshot agent. You show it a phone screen and it just knows exactly where a user should tap next to navigate an app. No way, right?
The biggest aha moment here is that these weren't explicitly trained tasks. Nobody gave the model a specific class on being a mobile UI agent. These skills organically emerged. Because the AI developed such an incredibly strong foundation in single image grounding during step 1 and complex multi-image reasoning in step 2, it just naturally transferred those skills to understand sequential iPhone screenshots in the real world. That is the true power of a unified model.
Finally, let's hit Section 5, Open Alternatives and Trade-offs.
Let's zoom out a bit to wrap up, because in AI architecture, there are always trade-offs, right? The amazing thing about LLaVA-OneVision is how accessible it is. The 2025 follow-up, LLaVA-OneVision 1.5, actually matches the performance of those massive, hidden proprietary models, but it totally democratizes the recipe. Fully open training data, open weights, open code. Developers globally can now take this exact budget and curriculum to build their own unified systems.
But there's always more than one way to crack a problem, and there are always architectural trade-offs. LLaVA-OneVision leans hard into fixed pooling and a highly disciplined budget. It actively trades configurability for high predictability. You always know exactly how much computing power it's going to consume. On the flip side, an open alternative like Qwen 2.5 VL uses a dynamic frame rate and a scaling budget, so a longer video physically uses more tokens. That gives you way more configurability for complex tasks, but obviously far less predictability for your hardware and your wallet. Which leads us to a final thought to close out today's explainer. As multimodal AI keeps racing forward at breakneck speed, what's the endgame? Will the future belong to models with strictly predictable, highly disciplined budgets like LLaVA-OneVision, or are we going to see the whole industry pivot to dynamic models that just scale up to any size? Damn the computational cost. It is a fascinating architectural battle, and it's going to define the very limits of the tech we use tomorrow. Definitely something to chew on. Thanks so much for joining me, and keep exploring.